So we're looking at the logistic growth model today, where the model is defined as this formula over here. So dp over dt equals kp multiplied by, all in brackets, 1 minus p over a. When we're looking at this, one way to think of it is, this is measuring the change in something with respect to, I don't know, maybe time. This is the exponential. Factor or part. And this over here is the limit. Or it restricts how high this model can actually go. Now, looking at what that means by example, if we have a look at the screen over here, there we go. What we've got is a Desmos model, and it's an LED or a light. Now, one way to think of it is, the more voltage that we try and push through this guy here, what you're going to find is the stronger the light gets. Now, this model that I've got it represented as is a linear model because it just goes up at a constant value. But reality is not really like that. So it goes up and then it plateaus, and doesn't matter how much more voltage you push through it, it doesn't get any brighter. In fact, it will probably just burn out, which younger me discovered. But that's a model that's sort of okay for this sort of thing, but it's not how these things really work. Rather, what you find is the curve is going to look not like that, but something like this. So at the very beginning, when you're pumping voltage through it, it's going to slowly go up. Then it gets into this window where it accelerates quite rapidly, and then it plateaus off. And it doesn't matter how much more voltage we put in, it just has no effect until finally we just fry the internal circuits because the voltage is too much and it just blows up. But this model over here that I've used to model this LED, this is the logistic growth model. So you can see that sort of goes up in a bit of, I guess you could say, exponential way. And then it just plateaus out, and it's got an upper limit of how high it can actually go. So this model over here is very similar to this over here. Now, what we're first going to look at in this lesson is, firstly, how we can describe this in terms of just P and A. Oops. So rather than writing this as a derivative, we're going to write it as just a function of P. And then after that, what we're going to do is we're going to have a look at how we can use this to model, I guess, population sizes. So first thing we're going to do is we're going to go through the algebraic method of rewriting this in terms of just P. So if we have a derivative of dp over dt, what do you think we're going to do to be able to get this in terms of P and T?
Bless you, Jack.
I needed to be blessed then.
Okay, we don't want dp over dt, so we don't want to see the rate of change. We just want to see an equation that models P in terms of T. So what we're going to do is we're going to move all the P's to the right side and all the things that can be with T to the left side. So in this instance, what we're going to do is we're going to say, firstly, K's can go on the left. So this is going to be, I believe, we'll just say K dt. And then, so I've multiplied both sides by dt, and then I'll divide both sides by this P guy over here and what's inside the bracket. So it's going to be P, then downstairs, oops, let's not write that. Let's go p 1 minus p over a. Then upstairs we're going to go dp. Do we see what's happened there? Alright, now because I've got fractions over fractions, I don't like that. So I'm going to just have a single upstairs and a single downstairs. We never want to have a 3-story house, it's just messy. So to do this, this is the same as saying, firstly what we'll do is we'll write this as a single fraction over here. So this is going to become p, then this will be a over a. And I shouldn't mutate this, but I will, because rather than having 2 fractions with same denominator, we can have a single fraction, single denominator like so, and then I can bring the p inside. So we go like that. Does that make sense? Now, if we're dividing something by a fraction, what do we do to the fraction? We flip it. So this is going to become a over p, a minus p, and then dp. And then the left-hand side is going to be k dot dt. And because we're in this form, we can, I guess, integrate both sides. All right. Now, the next trouble is, how do we even integrate a function that looks like this? Not easily. So what we're going to do is we're going to use a transform. Partial fractions transform, where the left-hand side here is equal to the right-hand side here. So we can actually split this sort of thing here, because, I'll do it here, and then I'll work on the other side. If we go p, a minus p, like so, our transformation is such that we can say this is the same as 1 over p. It's a plus or take, I believe it's plus, a minus p all over 1. Is that cool? And because we're able to do that, it's an easy transform to put in a form that's easier to integrate. So the integral of k dot dt is equal to the integral of 1 over p plus a take p dot dp. All right, now we can go for our integral. Integral of k with respect to t is just kt plus big C for our constant. This guy's going to be the natural logarithm of p plus the negative of the natural logarithm of a take p. Negative came from the negative on the p there. And then the plus c is already covered on the left-hand side there. Is that cool? From there, we can use our log laws. So these guys can come together. It's the natural logarithm of a take p under p, because they divide when it's take. And then this is still kt plus c. From there, we reverse it around. So a take p all over p. We remove the logarithm by raising everything to a base of e. So this is going to be e kt plus c. And this is plus or minus because we've opened up a logarithm, because it's got the absolute brackets there. From there, what we're going to do is we're going to flip this upside down. So a semi-articulated boss flip, which means that these are going to become negative. Do we see that step? So we just did a 1 over here. So we did a 1 over, and to accommodate for the 1 over, because we're working with indices anyway, just make them both negative. And then we're going to say let b equal plus or minus, so that's still plus or minus, e to the negative c. This gives us the effect of saying b at front, e to the negative kt, and then this here is going to be a over p. Take p over p is 1. From there, add 1 to both sides. Yep, that's right. And then we want to write it in terms of p, so we're going to flip it all upside down. And then we simply multiply it by the a. And lo and behold, there is your logistic growth model in terms of P and T. Any questions? All right, now the reason why we go through this really long algebraic process is because you're probably going to get at least one of these in the internal for this topic, because they appear every single year, and you're likely going to be asked to do the entire thing in the external if one of these questions pops up, because they always do it that way. But what they might do to try and stitch you up is sometimes they'll give it to you in this form, but the A over here won't be the A that you're expecting. So these two won't match up, so you'll have to add a constant. Last year, that's what they did in the internal. You had to have a factor outside to make it work. Any questions? Okay, so that's the logistic growth model, so the base form of deriving it. Now, next step is, sorry, that's the logistic growth model. This is effectively what it looks like. So there's always going to be a function that looks like this, where there's a limiting factor up here. In this case, the limiting factor is going to be there. Is that cool? So there's an asymptote. Does that make sense?
Yeah.
Alright, now let's have a look at an example. The population of an island is currently 154. Its expected growth rate is given by dp over dt equals 0.16p. In brackets 1, take p over 500, where t is in years. Write p as a function of t. Any ideas on how we do this?
I think we're going to do that.
Yeah, just do that. So we've got part A is dp over dt equals 0.16p. 1 take p over 500. And what we want to do is write this in terms of p. Welcome, Mr. Sweet.
Thank you.
First thing we do is we just use this method over here and apply it to that. So first step is, what are we going to isolate?
Our P's and T's.
P's and T's. So our constant, which is the k here, will move on the left here. So this is going to be 0.16 dot dt. Over on the right, we're going to have, I believe it will be, how can we write this? P 1 take 500 over P. Did I write that right? Yeah, okay. All right, now, modification to this. We have two terms inside. What should we do to the first term to make it look like the second term?
Single fraction.
Single fraction, so 500 over 500. Or a better way to put it, $500 take P. That's all over dP. Dog poo. Okay, next part. What we're going to do is change it so it's not a 3-story house, but a 2-story house. So that's going to be like so, dot dP. And then we use that transformation to break this fraction apart. So this is going to be 1 over P plus 500 take P all over 1 dot dP. And then we integrate both sides. Cool so far? Doing the integral, it's going to be 0.16 t plus big C. This is going to be ln of P plus negative ln of 500 take P. And then simplifying this using log laws, ln still okay? All right. Raise both sides to a base of E. And then flip it. So this is going to be 500 minus P over P. And then this is plus or minus E to the negative 0.16 T take C. So it's negative from the get-go because I did a boss flip from here to here, as well as raise it to a base of E. We let B equal E to the negative C. Hence, what we're going to get is 500 over P, take 1, the P and the P. This will be B, plus or minus by the way, E to the negative 0.16 T. Once we're there, we can just finish it off on the single line. This is going to be P equals 500. Downstairs, it will be a 1 plus B E to the negative 0.16 T. And there's our P in terms of T. Now we can do a little bit better than this. The question tells us the population of the island is currently 154. Its expected growth rate is given by the formula we've already got there, where T is in years. What is the starting population? Patrick?
154.
What year?
0.
Once more with confidence.
0.
0. So you can simply sub in 154. And then that's 1 plus B, E to the negative 0.16 times 0, 500. And then you could solve that. Now what's the most efficient way to solve that? Yeah, just use your calculator and the solve n function. What did you guys get?
173 over 77.
Yeah. So E is going to be 1 plus 173 over 77. So there's your model there. That's part A. Part B, find the population after 10 years. How would we do that?
Sub T is 10.
Yeah. When T equals 10, then your population is going to be times the 10. Answer?
344.
Okay, so this is a reasoning and communication one. What is the population going to be after 10 years, and why do you think this? 343, 344. Why do you say 343, Patrick? Yeah,
That's true.
at least. So it's, I wouldn't say guaranteed, but it's more likely to be 343 and one pregnant person. Or someone got attacked by a shark. And they've lost the limb. Okay, find the time taken for the population to increase to 480. Again, how would we do that one? Yeah, just use solvent. And then the final one. So we're going to skip C. Final one. What is the maximum population size going to be? How would we solve that?
When T approaches infinity.
Bingo. So this one, tick all the stage ones is, what we're going to say is P, so this is going to be the limiting P, is going to be 500, 1 plus 173 over 77, e to the negative 0.16 t. And then what we're going to do is something really fun. We're going to take the limit as t gets really big. So we're calculusing for this. What happens when t becomes enormous?
E becomes really little.
This guy becomes really little because it's negative, which means this is basically 0, which means this is
0.
0, which means that this is 500 over 1. Another way you can do that is just start subbing increasingly large numbers in for t until you find what it trends toward. And that is your horizontal asymptote. All good?
Yeah.
Do we understand why we took the limit?
Yes.
Will you be able to do that on an SAT?
Yes.
That's literally as hard as it gets for this topic. Well, not this topic, this lighting intention. It's actually not too bad because we've done all of this stuff before.
That's all method stuff.
Yeah. Any questions?
Nope.
All good? Alright, so I think it's questions 1 to 6.